So here's where linear algebra starts to get a little weird. We have what's called the span of a set of vectors. So we write the notation as span set, and then we write our list of vectors that we're spanning. So the span of a set of vectors is the set of all linear combinations of these vectors. So if you have a set of vectors, and if you can think of every possible way that you can combine them together in a linear combination, meaning you put different weights or different coefficient scalars in front of those vectors and add them together, what are all the different ways you can do that? So let's start with, let's just span a single vector. So let's just say we have one vector. Let's say it's in R2, okay, just so we can visualize it. In R2, I want to scale a single vector. So let's say this is the vector. So that's u. So what are all the ways you can write u as a linear combination? Well, u would be, well, let's say this, the span of u would be equal to the set of all vectors where it's some constant times u, where that constant is a real number, a scalar. So it's just a single vector u times a scalar, meaning it's just scaled versions of u. So if I multiplied u by 2, right, I would get this vector. If I multiplied it by 1.5, I'd get this vector. If I multiplied it by -1, I would get this vector. Sorry, this vector. That would be -1/2. And if I multiplied it by -2, I'd get this vector, right? And you can see I didn't draw those exactly right, but the span of a single vector in R2 is just going to be a line. Do this a little better here. There we go. Right. So span of a single vector is just going to be a straight line, okay, in R2. So let's see what happens when we span two vectors. So let's say we're going to span u1 and u2. So let's say that u1 is here and u2 is there, okay? And I'll pick a different color for the spans. So if I just add these two, right, I'm going to get this vector, right? What if I multiplied the first vector by 2 and left the second vector the same and added those? So this would be 2u1 plus u2. That vector would look different, right? So that vector would be here. What if I multiplied u1 by -1 and u2 by 2? I'll get this vector. and I added those up. That's going to be here. And you can keep doing this, and eventually you can get every single vector in R2. Right, so you can add different combinations of these two vectors as long as they're not on the same line. If these two vectors are not on the same line, if you span them, you get the entire R2 plane. So this is a plane when you span two vectors. So in this question, we have x1 and x2 and vector b, and it says determine whether b is in the plane generated by the span of x1 and x2. So x1 and x2 are in R3, right, three-dimensional space. And if I span two vectors, I know I'm going to get a plane. So if I span these two, I get a plane, a two-dimensional plane in three-dimensional space. And I want to know, is B in that plane? So if it is, it's one of the linear combinations of x1 and x2. So it means that, there's some a1 times x1 plus some a2 times x2 that will give me vector b. Right? And we just learned in vector equations that we can rewrite this as the system x1, x2 augmented with b, and we're solving for these variables a1 and a2. So again, I'm going to use my calculator. It's 3 by 3, very similar to the last one we did. I'm going to use the RREF function on matrix A, and I get this. So we'll say this is row equivalent to and this is where it's very important to realize where the augmentation happens. So this is the augmentation line. That's where these two things are stitched together. And these are the variable coefficients, right? And this here says that 0 plus 0 equals 1. Right? 0a1 plus 0a2 equals 1, and that can't be true, right? So this is a no solution. So what that means is this vector b is not in the plane that you get when you span these two vectors. So we'll say b is not in the plane, right, that you get when you span x1 and x2.